That you can say about basically any talk I give. You didn't read the title, did you? Okay, so good. So I'll talk about
indexing irreducible polynomials.
Good. Yeah, that's it. Indexing irreducible polynomials. Over finite fields, so over F. And this is joint work with my student Mrinal Kumar. And Mike Sachs. Good. Okay, so I defined the problem in my abstract. Let me just say it very compactly. So I'll tell you what indexing a set means. Okay, so I have a set S. An indexing of a set, an indexing of S is a map F from 1 to etc. up till size S to S. Okay, just any map. So it's a map like this, a bijective map. Okay, that's it. It's just some arbitrary bijection between the set between 1 to 3 up to the size of S to the set S. Okay, and the problem for this talk is the following setting. So we have Fq, the finite field of Q elements. We have an integer n. Okay, and we look at S, the irreducible polynomials. Monic, one variable, so in Fqx of degree n, and the question is index this set. Okay, so S is a set of irreducible polynomials of degree n, monic, and we want to index it. So find a way of giving names to all the irreducible polynomials, 1, 2, 3 up to something. Okay, and so first of all, I think it's quite a natural problem. So over the at least growing up, I heard people ask, "Oh, is there a formula for the primes?" in various popular books. So it's something like that. I'm giving you names for all the irreducible polynomials of a given size, degree n. Good. And so it's not just given indexing. So ideally, we would want the indexing map should be efficiently computable. Okay, so this is the problem that I'll try to solve.
Now do you mean just the map is efficiently computable, or its inverse also?
No, so I don't mean the inverse. So one can ask a closely related question, which we call it a reverse indexing. Reverse indexing a set S. S is a map F from, maybe let's call it G, from S to 1, 2, 3 up to S. Okay, so I said, oh, it's like giving names to every irreducible polynomial. Actually, reverse indexing is like giving names to every irreducible polynomial. The indexing is like giving irreducible polynomials to every name, right? So do you understand that these are different questions? Find an efficiently computable map from 1 to 3 up to S, and find an efficiently computable bijection from S to 1 to 3 up to S. And you can also ask, find a map where both are computable efficiently at the same time. And yeah, so I don't know, one question.
Reverse indexing you can do by hashing or something.
Oh no, we're talking exact, approximate. Yeah. So I'm in a totally exact world for this talk. So.
Are there any applications for these things?
Are there any applications for these things? So occasionally, So there have been several papers where the problem, there are many constructions of the form take an irreducible polynomial and do something with it, and often the irreducible polynomial is part of the seed to some construction. So I know there's one very nice epsilon bias set constructed in by Alon, Goldreich, Hastad, and Peralta, and which requires you to have a name for every irreducible polynomial. So something like this would solve the problem which is needed in that. So and there have been other situations where things like this have been needed, string matching and things like this.
Do you think of Q as larger than N or similar size?
So N is certainly very large, and Q can be at the same size as N or smaller, and it could even be larger. Yeah. Good. Yeah. So this problem has popped up in various situations when people did constructions with irreducible polynomials, and it annoyed them, and people found a way around it. But I think it's quite an interesting and natural problem by itself.
So I think you know how to find even one irreducible polynomial?
That's a very good question. So here's another problem. We got a bit ambitious, didn't we? Right? We said. Let's find an indexing of all irreducible polynomials. Can you find even one? So here's the problem. Given n and q, find an irreducible polynomial in fqx of degree n. Right, and we don't know how to do this deterministically in polynomial time. But we do know how to do this, so it's only known how to do this. In time. So what is polynomial time, by the way? So we want a polynomial of degree n, a q coefficient. So n log q is the running time. So we would like it to run in time poly in n log q. So we don't know how to do this. We know how to make this run in time poly in n characteristic of fq and log q. So if q is prime, we don't know how to do this. But if q is a high power of 2, for example, then we can do this in polynomial time. Okay, so then it's reasonable to try to solve it.
This is due to some Riemann hypothesis?
No, this is unconditional. Right, with the Riemann hypothesis, then we can do this in time n quasi-poly log in q with the Riemann hypothesis. Yeah. Okay, so yeah, so how are we going to solve this problem of indexing irreducible polynomials? So I didn't say what the theorem was. So the theorem is going to be there is an efficient algorithm for indexing S which takes a little bit of advice. Okay, so it takes a little bit of advice. How much advice? It's going to be just enough advice to specify an irreducible polynomial over fq. Once you give me enough advice to specify one irreducible polynomial over fq, that will be enough to do the indexing. So that's what the theorem is. I'm using a board.
Advice means non-uniform.
Non-uniform. Yeah.
That's what.
Yeah. I'm using a boards really fast. Maybe I'll start writing smaller. Good, so theorem. There is a poly in n log q time algorithm for indexing irreducibles of degree n over fq. That takes n log q bits of advice. Right? That's the theorem. And so this is consistent with the fact that we don't know how to find a single irreducible polynomial, because this n log q bits of advice will give you an irreducible polynomial. So there is a so this result can be improved if the characteristic of the field is small, because.
But we need at least a characteristic to specify one polynomial.
Or no, but log q is at least the characteristic. Wait, yeah, log q is at least the characteristic. Yeah. So that's.
Is the advice just one irreducible? Can you say if I have one irreducible polynomial, I can index them?
No. So that's a bit or too optimistic. No. So it's not true that if you just give me any old irreducible polynomial, then I can do this, solve this. But if you give me a pretty decently good irreducible polynomial, then I'll be able to do this. So I'll tell you very soon what this advice will be.
A random one.
It will be a primitive polynomial of the right kind. So it will, good. Oh, because sorry. So we know how to do it in time poly in n and q. This is even better than that.
I mean, even if for q is at least a characteristic, then we don't need it.
That's not true.
Q is always at least a characteristic.
Yeah, either you don't need it here or you don't need it.
Okay, so I didn't understand the question maybe.
Okay, the characteristic
Yeah.
so log q is at least the characteristic.
Yeah. Oh, no, it's not.
Log q is just a characteristic.
No.
You don't need it.
Q could be equal to the characteristic.
Yeah, so let's say, okay, so never mind that. I'll take that back. That's true.
The maximum. That's the same thing. Where you are.
Yeah. So the fastest we know how to do it is time poly in n and q.
Okay.
Right. So we cannot hope to solve this in time poly n and log q.
Okay, so you need at least poly n q with some class.
No, that didn't say that. It just said that the running time here should be poly in n and q if we wanted to do this. Good. So let me say something about small characteristic also. Just all right. So just and if characteristic of q, or characteristic or the field itself. Let's say if q equal to 2, then need log n bits of advice. Even though we do know over fq how to produce an irreducible polynomial in time poly n. So this is not consistent with, I mean, this potentially, if q equal to 2, potentially we could just solve the problem, period, without any advice, but we don't know how to do it. Okay, so that's the theorem statement. This is an indexing, it's not a reverse indexing. We don't know how to do a reverse indexing. Reverse indexing would require discrete log for whatever we're going to do.
But if you solve the bits of advice, you can go over all possibilities.
With log n bits of advice, you can go over all possibilities of what?
Advice.
Oh, correct. But but this indexing problem is a funny thing. You can't verify that you have the right indexing, right? An indexing problem is it's an algorithm. It's for every I that it's given, it produces an irreducible polynomial. So, but yeah, you can go over all bits of advice, but you still have to produce one answer when you're given an I. So that doesn't let you get rid of the advice.
So why do you need much less advice when q is 2?
For the same whatever reason happens, whatever reasons we use this advice, it has to do with that.
Okay.
Yeah. So okay, good. Any questions about the theorem statement? Yeah, so we don't know how to do reverse indexing or a map that's simultaneously both an indexing and reverse indexing, both we don't know how to do. Okay, so let me tell you how it's proved. So I'll be able to prove the whole thing hopefully. Okay, so So where are the roots? So very quickly I'll do some stuff with this setup, do some algebraic stuff, and we'll reduce to a combinatorial problem. The combinatorial problem will have to do with necklaces, which are strings which are equivalent under rotation, and then the rest of the talk will just be the combinatorial problem. So how do the roots of an irreducible of degree n in FQ, where are they? Well, they lie in FQ to the n. Right? So take some irreducible polynomial p of x, and alpha is a root of p. So instead of indexing the irreducibles, let's try to first index the root. Start with the root and try to get the irreducible out of that. Okay, and you can index the elements of FQ to the n quite easily. How the elements of FQ to the n are just, I mean, this is just isomorphic to FQ to the n, and you can find that isomorphism if you know a construction of FQ to the n over FQ. So yeah, so indexing the points of FQ to the n is quite easy. Right, but one irreducible polynomial of degree n. So let's say we got that as advice, for example. So we use one irreducible polynomial of degree n. It helps us construct the field fq to the n. Good. So once we have that, maybe we can just pick a root in fq to the n and look at the polynomial p of x for which alpha is the root, and then take it from there. So there's a map from fq to the n to polynomials over fq, where you take alpha and you map it to the minimal polynomial of alpha. Over fq. Okay. That's not a bad map. Okay, and maybe we can now try to ensure that we choose alphas in a good way so that we get the irreducible polynomials of degree n. Because the minimal polynomial might be something smaller, but we want to make the minimal polynomial have degree n, so maybe we can choose the alphas which are primitive to fq to the n, so the ones which actually have minimal polynomial being degree exactly n. Okay, so let's see what does it take for this to happen. So the minimal polynomial of alpha in fq to the n has degree n if alpha is in fq to the n but not in fq to the m for all m less than n. So this if we can get our hands on alphas which are in fq to the n but not in any of the smaller subfields, then the minimal polynomial alpha will have degree n. Is that okay? Then good. So suppose we got our hands on that. We're still not done, because every irreducible polynomial will be produced by many different alphas. There are many alphas that will lead to the same irreducible polynomial. Okay, so if alpha has minimum polynomial p of x, then so does alpha to the q, alpha to the q square, alpha to the q to the n minus 1. All these other elements, their minimal polynomials will also be of degree n, and they will all lead to the same polynomial p of x. So this won't give us a bijective map between the set, between a nice set and the irreducible polynomials. It will give us a n to 1 map from a nice set to the set of irreducible polynomials of degree n. Good. So we need to somehow break this symmetry. We need to choose from each of these collections, alpha to the q up to alpha to the q to the n minus 1. We need to choose one of them. Yeah.
Aren't there many copies of fq to the m inside fq to the n? What do you mean?
No, there's only one copy of fq to the m inside fq to the n. Yeah. Good. Okay. So good. Okay. So I'll do some steps bit non-deterministically, but then but then it will be clear what the combinatorial problem is. Okay, so consider alpha to the q, alpha to the q square, etc. up to alpha to the q to the n minus 1. Write them as g to the I1, g to the I2, etc. up to, or maybe that's I0, I1, etc. up to g to the In minus 1, where g is a generator of fq to the n star, and I1, etc. up to I0 up to In minus 1 are integers in q to the n minus 2. Every element of the finite field fq to the n can be written as a generator to some power, all these non-zero elements. So represent them in this fashion. We have alpha to the q, etc. alpha to the q to the n minus 1. We write them as g to the I0, g to the I1, etc. g to the In minus 1. What can we say about I0 up to In minus 1? Right? How do they so we are looking at elements which are q conjugates of each other in this fashion. How do their exponents look? So this is I0, this is I1 is I0 times q. So it's right. So this is so Ik is equal to I0 times q to the k, but I want you to write it as g to some power mod, I want you to reduce that mod q to the n minus 2. So it's actually I0 times q to the k mod q to the n minus 1. So we took a number, we multiplied by q to the k and reduced it mod q to the n minus 1. Now if you write these numbers Ik in base q, this corresponds exactly to rotating the base q representation of the number I0. If you take I0, you multiply by q to the k, in base q that's just adding a bunch of zeros at the end, and then you reduce it mod q to the n minus 1, that just bringing the part that went ahead back. So let me draw that. I0 is here, and I0 times q to the k is, I guess, 0 0 0 0 0, and then mod q to the n minus 1, so it takes this part off and it brings it over here, it replaces the 0. So okay, so this is exactly rotation.
So also you can also do this by taking a basis of fq to the n over fq, where the basis is x to the q, x to the q squared. And also raising to the q rotates them.
Right, if you take a normal basis for fq to the n, then raising to the q rotates elements. That's right. Yeah. Good. So what we learned so far is that so now elements of fq to the n, let's try to represent them as powers of g. Then the elements that correspond to this bundle, alpha to the q, etc., alpha to the q to the n minus 1, are precisely rotations of a single string of length n. And if you want to pick just one element from this bundle, right, remember we want to pick irreducible polynomials. So to pick irreducible polynomials, we need to pick one element from each bundle. To pick one element from each bundle, we need to pick one element from each of these rotation classes. So we're down to the indexing problem for necklaces, and that's what we'll solve for the rest of the thing.
And the good alpha, the one with the minimum polynomial is degree n, or is those that the only rotation where they're equal to themselves is the n when you rotate it n times?
Right, exactly. So there, good. So that final comment was, so there are going to be some strings I0 such that when you rotate them not n times but maybe n over 2 times, you see the same string. Those correspond to alphas which lie in the field fq to the n over 2. Okay, and those also were ones we wanted to avoid. We wanted to index only the irreducibles of degree exactly n. So what we are down to is indexing necklaces of period exactly n, and that's what the problem we have to solve. So let me write that down. So necklace. So
What's the definition of a necklace?
I'll say that in a second. Good. So, in fact, now necklaces are strings in sigma to the n mod or equivalence classes of strings in sigma to the n mod rotation. So you identify two strings if they are rotations of each other.
And sigma here will be?
Sigma will be q, 1 to 0, 1 to 3 up to q minus 1. We took the base q representations of the numbers I0, and those are the things that will be, yeah, those are the necklaces, the alphabet for the necklaces that we need to deal with. So for us,
Wait, each ik is an element of q to the n, right?
Right, each ik is in this set.
Yes.
Now we write it in base q.
So each I is an element of an n.
So let me say that again. Each I0 is a big integer. It's between 0 and q to the n minus 2. But if you write it in base q, it's a string.
Yeah, like that.
Right. And I0 and I1 correspond to rotations of the same string. And we need to get one of them. Out of all these I0 up to in minus 1, we need to just get one of them. So we need to index necklaces with over 0, 1, etc. up to q minus 1 of period exactly n. Necklaces over this of length n and period exact. So that's the problem, which if we solve that, then we can index irreducible polynomials of degree exactly.
How do you find the roots given the polynomial?
Oh no, we don't have to find the roots given the polynomial. We have to find the polynomial given the root. So good.
How do you do that actually?
Well, that's linear algebra.
Yeah, that's linear algebra. Then you take 1 alpha alpha square up to alpha to the n minus 1 and find a linear relation amongst them over fq. Good. So the index.
Multiply x minus alpha on x minus alpha.
Oh, great. That's another good one. Yeah. So you can also multiply x minus alpha to the q, etc. Good. So how does our overall algorithm look? So suppose we have solved indexing for necklaces. So use your integer from 1 up to the number of necklaces to pick a necklace. Take that necklace and treat it as an integer. So treat it as a base q expansion of an integer between 0 and q to the n minus 2. Consider g to the power that, where g is a generator. Where do we get this generator from?
From the advice.
From the advice. So the advice is a generator of fq to the n.
This is also like a random element would do, right?
Well, not with such great probability, and this is an exact problem, so it may be just safer to.
No, if you can replace like advice with randomness.
Oh right. Oh, I agree, but we can't verify that an element is a generator. Okay, so that may not be a problem. A random element is a generator with decent probability, yeah, and the advice we need is a generator. That's all.
That's all you need.
So it's a generator, and we also need the construction of the field fq to the n over fq. You can do both at the same time by giving the minimal polynomial of a generator. So that's called a primitive polynomial. So with n log q bits, you can give a primitive polynomial.
You can do it randomly and hyperbolic.
No, well, the problem that you had, well, it might be random, is that you need factorization of q to the n minus 1 to verify it's actually primitive. So,
No, without verifying, let's just say I just want to, with high probability, give.
with high probability, but.
So
without verifying.
Without verifying.
So you can.
The probability of the third column is like 1 over n or something? That's right. Something like that.
Oh, it's too small.
It's 1 over phi.
Right. So it's not that great probability. And anyway, we don't have one output for this problem. At the end of this, you have to produce an indexing algorithm, and so that you're not going to use fresh randomness for each time you're given an I how to produce the corresponding irreducible polynomial. So the advice is a generator. And the generator comes in terms of the minimal polynomial of the generator, which simultaneously gives you the field fq to the n, and it also gives you a generator in the field. So that's the only use for the advice. We'll solve the necklace problem without any advice. Well, it's a very basic combinatorial problem. Okay. So we looked for so once we came to the necklace problem, we actually started looking quite a bit for, surely, problems like this are looked at. Anyway, so turns out that no, and there's a whole community of combinatorial enumeration where they enumerate objects and they rank objects and things like that. But this was one of their open problems actually from several years ago, so maybe 20 years ago. So yeah, so the indexing of necklaces, but we didn't know that fortunately. So it.
Do you know how many necklaces are there?
How many necklaces? Yeah, the number of necklaces of length n equals the number of irreducible polynomials of length n. By that. The number of irreducible polynomials of length n, well, there's this inclusion-exclusion formula, and in fact, you could have done it directly at the necklace level. So there is a formula.
So you don't understand it when it's a prime? Sigma is a prime?
No. So we can do it in all cases also now.
I see.
Yeah.
So this sort of the correspondence works for positive numbers?
Oh, no. The correspondence, no. Whatever proof you use to count the number of necklaces of length, then you can just do that directly with some inclusion, exclusion, Mobius stuff, which we will also see.
In fact, that's on the top of the board, that's the inclusion, exclusion.
Right, getting rid of all the fields fq to the n. Yep. Okay, so we wrote a paper. It appeared in iCalc. At the same time, this problem was also solved in the combinatorial enumeration community. I don't know why they waited for us, but yeah. So it was solved also by. I have this one second.
Long name. So only notes for the talk.
Yeah.
Okay.
Good. Yeah. Good. So, and they also solved the enumeration problem for the indexing problem for necklaces, and also the reverse indexing problem for necklaces, and whatever we do will also solve the reverse indexing problem for necklaces. So necklaces, actually we can do a lot of things algorithmically, but with irreducible polynomials, the reason why this isn't a reverse indexing is because you need to do discrete logs. If I gave you the irreducible polynomial, to find that integer, you would have to take discrete logs to go from that representation to that. So okay, good. So let me write the necklace.
If you do indexing, as I said, with a normal basis, then you don't have to do discrete log. The basis is x to the I.
How do you identify elements which are not in fq to the n minus? Oh, I see. Okay, maybe. So let's talk after this. Okay, good. Okay, so many things can be indexed very nicely, but the trickiest problems for indexing are ones where there's some set of objects which is naturally counted, but there's some group of symmetries, and you want to choose one element from each equivalence class. Somehow this has a lot of meat in it. Anyway, so goal to index necklaces. Yeah. So more precisely, one element from each rotation class in sigma to the n. Each rotation class of a class of full period n, but that will come automatically. So a sub goal is, and this will enable us to do the indexing. Is going to be some kind of counting problem. In order to identify the 500th rotation class, we'll try to count the number of rotation classes less than a given string, where you take lex order or something like that. Okay, so let's do the following. So counting. So given x in sigma to the n, find the number of necklaces C such that the smallest element of C is less than x in lex order. Okay. If we can solve this, then we can index necklaces, I want to say. Why? Because so then we'll binary search on x, and let's say we want to find the 500th necklace, then we'll binary search on x, we'll look at x, we'll count the number of necklaces C which have one of their smallest elements, its smallest element less than x. If that number is bigger than 500, we go down, and then we keep moving x until we find until the answer to this problem is 500, and then that's our 500th necklace. Yeah, so how do we count necklaces? We want to find the number of necklaces which have their smallest element less than x. So what we'll look at is this. So I'll make some definition. So A x p is the set of all necklaces C such that C has period p and the smallest element of C is less than x. Okay, so there are many necklaces whose smallest element is less than x. Some of them have period n, some of them have period n minus n over 2, etc. The period always divides n. So we want to try to distinguish between them. That's a good start.
So in this count, you want to count only period n? For the algorithm that you said before.
Oh, right, good. Find the number of necklaces C of size n, of period n. Good. So we let AXP be the necklaces C so that C has period P and the smallest element is less than x. AX at most P is the necklaces C such that C has period period dividing P and smallest element of C is less than x. So it's the same thing except it's you also count the necklaces whose period divides P. So AXP what we want is something like AXP. But it's easier to count things like AX less than or equal to P. So size of AX less than or equal to P is the sum over all D dividing P of AXD. So size of AXP, let's call this D, sure. Sum over all E dividing D, mu of E, AX, or maybe this is D over E, AXE. This is the Mobius inversion.
Okay, why can you restrict version to just d dividing p?
Here, because well, first of all, the definition was we're looking at those whose period is less divides p.
Oh, not okay. Divides p.
Right. Okay, maybe I should have called this ax less ax divides p.
Okay.
Yeah. Okay. Yeah. Oh, sorry. This was less than or equal to.
Can you just say what this function is?
Good. And good. So whenever you have a formula of this form, f of n is sum over all d dividing n f of d, then you can express, oh sorry, g of d, then you can express, so let me say that again, f of n is sum d dividing n g of d, then you can express g of n as sum e dividing d of d mu of d over e f of e, where mu is the Mobius function, mu of n equals -1 to the number of prime factors of n if n is square free, meaning it has no prime square factors, and 0 otherwise. And this is called the Mobius inversion formula. Okay, so how do we count the number of strings whose period is at most e, or whose period divides e, such that some element of that necklace is less than x. So let's look instead at the following, which is very closely related. Gxp is the set of all y such that in sigma to the n, such that some rotation of y is less than x and period of y divides p. What's the difference between gxp and ax? Gx less than or equal to p and ax less than or equal to p. Gx less than or equal to p is just the union of all the necklaces in ax less than or equal to p. Ax less than or equal to p was the set of necklaces. This is the set of strings. Okay, so we just take all the strings from all those necklaces and put that into gxp. And we want to count the number of strings in gx less than or equal to p. Good. So what we'll do is we'll construct a branching program or an automaton that can recognize strings in this set. Once you've constructed a branching program that can recognize strings in this set, then you can count the number of accepting paths, the number of accepted strings by the branching program by a simple dynamic program. So the tool that we'll use is, so can count in polytime the number of strings accepted by a branching program. And so the goal is, so new goal, design a branching program
Just in a finite automaton.
which is just a finite automaton. Which accepts, which recognizes gxp. Okay, so what's the mechanics? We're trying to design a polynomial time algorithm that it takes x as input and it outputs a branching program. It doesn't have to run the branching program, but once it outputs this branching program, it can we take our separate algorithm which can count the number of accepted strings by this branching program, and it will output that answer, and it will just give you the count. And then this feeds into the binary search that we were doing. So this is the overall shape of the necklace indexing algorithm.
This has to be a deterministic.
It has to be a deterministic branching program, because you want to count. Yeah. So the number of accepted strings should be correspond to one path in this branching program. So we want to design a deterministic branching program. So there's a sum rotation of y in there. So you want to accept strings y such that some rotation of it is less than x. Yeah, that's a funny condition. So it has to be read once, pass through. Oh, can it be string matching? Yeah, that's. Yeah, so we'll do some kind of string matching. Yes. When is some rotation of y less than x? Give me a condition on y so that some rotation of y is less than x. Okay, so here's x. That's x, and there's some y here, and we're in lexicographic order, so the first bit matters the most. Yeah, so this is y. Some rotation of y will take maybe this particular location and bring it to the front. So now it looks like, so let's say this was here, so now this is here. And if this is less than x, then you're asking that some prefix over here happens to be less than the prefix over here. Okay, good. So I'll say that the answer to this is, well, how could so what prefix here is less than some prefix here? Well, they must agree up to some point, and then finally you see a character which is less than what you saw, then the corresponding character of x. So let me do the following. So here is x. I list. So I've gone to binary just to make things neat. So here's x. I list the following strings: 0, 1, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 0, dot dot dot. If any of these strings appears in y, then some rotation of y is less than x. So these are the strings less than some prefix of x, the maximal strings maybe. Okay, and I'll call this L sub x, and if any element of L sub x is present in y after rotation, possibly, then some rotation of y is less than x. Okay, so it's a matter. So the question is, design a branching program that will take in a y and detect whether it contains one of these as a substring.
You mean read once, right?
A read once branching program that reads. I should have said read once branching program. That was important for those who know what branching program means. I meant read once branching program. If you heard automaton, then it's automatically that. Good. So we want to design a read once branching program that reads in y and it detects whether any of these strings is present as a substring of y, but possibly with wraparound. So I mean, if y is here and you found one of these strings over there, then okay, great, and presumably you could do this easily. But just to be precise, we also need to worry if the substring is present with a wraparound, because we're looking at general rotations. Okay, so we need to design a branching program that can catch substrings present inside, catch all those y's which contain a given substring either contiguously or with wraparound. Okay, and good. So that's the final problem that we need to do, and it's not difficult, but that's what we've reduced to. So did everybody follow what this reduction was? So I took the string x, I looked at the longest prefixes of, how do I say this?
I think it was clear, so I don't think we need to.
Okay.
No, just say it again.
Okay, good. We're looking at, so take a prefix of x and take a string which is just one less than that. Look at all such strings that you get. One of these must be present in any y which is less than x. Any string that is less than x must start with one of these strings. So that's the set Lx. Now we're interested in finding all those y's which contain one of these strings somewhere inside y, possibly after rotation, possibly with wraparound. Good. Okay.
You can try to count this directly, not going through branching programs.
Try to count these directly. I agree.
Dynamic programming.
Right, with a dynamic program, but it will end up being the same because the counting algorithm for branching programs is dynamic programming. Yeah. So we want to design a read once branching program. Which accepts, yeah?
In this case, you just get all the y's other than the all one string. Right? You get all the y's that have a 0 in them.
Because this starts with a 1.
Right.
Right, good. Right, so but then all this means is that the heart of the binary search will happen with x's which start with half zeros maybe.
Right.
Once you have an x which starts with half zeros, then there'll be interesting stuff going on. Yep. So design a read once branching program which accepts all y which contain as a substring an element of Lx, and Lx is a polynomial size string set. It's just in fact size n. Okay, and the design is the algorithm will produce the read once branching program. So it should be a construction of a read once branching program which an algorithm can output in polynomial type, which will all be clear once we do it. Okay, so we've all constructed in automata, or at least we've taught that yeah, you can recognize all strings which contain ABBA, for example, as a pattern. Now I have a collection of poly n such strings, and I want to recognize if any of them occur. Right? And right, so I'll say it in one sentence. Let me try to say the right one. So keep track of the longest. So I'll first do so we'll do it in two parts. One is for contiguous substrings that occur like this, and then we'll also do it for wraparound substrings by a different branching program, and then you'll take the product of the two. So keep track of the longest prefix or suffix of what you saw so far, which is a suffix, which is a prefix of something in Lx. So, yeah, that's it. The longest, so you saw something so far, you're processing the bits of y as they come. Keep track of the longest suffix of that, which is a prefix of something in Lx. And this is something you can immediately define a branching program for. The prefixes of things in Lx, well, Lx is a set of size n, the prefixes of things in Lx is a set of size n square. Okay, so that's something you can maintain. And okay, and this, so this gives a contiguous matches.
Okay, so does this use the fact that this is a prefix though?
No, it doesn't use that. For any set of strings, you could have found contiguous matches just by keeping track of the, as long as the size of the set is polynomial, you can do it by keeping track of the longest suffix of what you saw so far, which is a prefix of something in your set. It would run exactly the same. For wraparound, you have to keep track of the, well, you have, okay, let me just say it in one sentence. And so wraparound matches. We'll keep track of two things. One, the largest thing from the front and the largest thing from the end. So keep track of the largest prefix of what you saw, which is a suffix of something in Lx. This part will keep track of the, so this is the y which we're reading. It will keep track of the longest thing over here which matches some suffix of something in Lx. Okay, so this is not bad. And also keep track of the largest suffix of what you saw so far, which is a prefix of something in Lx. So yeah, so well, if it's an automaton, so you keep reading characters of y, I mean you're marching along, you don't know if you've reached the end yet, you're anticipating the end, but what you keep track is the largest suffix of what you've seen so far, which could be the prefix of the wraparound string. So it has to be a prefix of something in Lx. So that's what you also keep track of. So you keep track of this, you keep track of this. At the end you have, take this largest match, you take this largest match, and from that you can decide whether these two together imply that you contain a wraparound string. Yeah?
I think, couldn't you do it a little more simply? It might not be sufficient by, since n, you can take poly and n,
yeah,
you could just guess where, you make an automaton for each guess where it is, and then you just have recognize the union.
No, we want a deterministic automaton, not non-deterministic. So because we want to accept every string, so ultimately we're interested in the count of the strings that are accepted. And so every string that gets accepted should lead to one accepting path in this automaton. So if we make a guess and do it at least the direct way, I think you have to maintain for each of those n different automata what's going on. And so that state is something to the power n. The size of the state space becomes something to the power n, which becomes too big. That's my guess. So we did try various simpler things. As far as we know, there's nothing simpler that works. But yeah, maybe after this we can talk. Yeah, good. Yeah.
So is there a chance that the largest prefix in largest subsets may not match.
May not match?
Yeah, I mean.
Oh, they may not come from the same string in LX? Yes, but you know the longest thing that could possibly be relevant, and you know the.
It may not have the longest suffix and prefix together.
I understand. So here's your string y. You remember, you know this is the, you know that this is the longest prefix, which is a suffix of something in LX. This is the longest suffix, which is the prefix of something in LX. But from this data, you know this entire explanation, you know this entire thing. So from this you can tell, oh, maybe inside this there was a match. So I mean, once you know all these characters and you know all these characters, and you remembered all these characters without actually having to remember all these, all the, I mean, if you had to actually remember the last A and the first B of these characters, you would have spent A plus B bits of memory, which would have been 2 to the A plus B states. But instead, you're just remembering these last A characters by saying, oh, it corresponds to this prefix of something in LX, and this corresponds to this suffix of something in LX. So you can remember it with just much fewer bits, log n bits. And then from that, you can identify whether it contains, I mean, you know which string this is. So you can identify whether this part and this part maybe make something in LX. So did that answer the question? I mean, you're remembering the largest possible thing that could possibly be relevant. And remembering a longer thing only tells you more information, because you are remembering the prefix of y and the suffix of y. So it's not that you chose to go remember this prefix and not that. Good. Okay. So from this you can count. This produces the branching program. The branching program can then you can use the branching program to count the number of y's which are less than a given x. Then this lets you do your binary search, and then it feeds into the. So that lets you index necklaces. Then that lets you index irreducible polynomials. Good. So yeah, in general, indexing and reverse indexing, I think they're very neat questions that could be asked and answered around here. Yeah.
So can you do reverse indexing just for the necklaces?
Yes, because this gives a ranking algorithm. So given the integer, you can also go back and
the same counting.
Right. Yeah, so indexing and reverse indexing, I think they're pretty neat notions, because it's not like the notion of ranking where you find the 200th lexicographic element. It gives you freedom in choosing the bijective map, which I think lets you gives some interesting questions. So two nice questions that I don't know how to answer. One is, can you do an indexing of all isomorphism classes of graphs on n vertices? And so I don't know, but it would be nice. And in case you're worried, it doesn't imply the graph isomorphisms in P, as far as I know. But reverse indexing of graph isomorphism, that would lead to graph canonization, which shows the graph isomorphism in P. So I don't know. I think that's one good question. Then there are other questions about just general complexity of indexing. So in order to be able to index a set, you need to be able to count the size of it, because I mean, implicitly your indexing algorithm should know the size. Yeah, so I don't know, is every set which can be counted, can it also be indexed? So a lot of these things seem like the answer is no. The paper is recently put on the archive, and there we answer a few of these questions, but many of them we don't know how to answer, and so it would be nice to do this. Another question that recently, so we tried a little, but is, yeah, suppose you can find an indexing of a set and a reverse indexing of a set. Is there a simultaneous indexing and reverse indexing of that set? Meaning it's one map for which you can compute both directions. So again, probably all these answers are no, but it would be nice to know why. Good, so that's all I had to say. Yeah?
What was known about this necklacing before? I mean, I would think that people have looked at similar problems or something.
Oh yeah, so people studied necklaces a lot. So there are some very, very nice algorithms for enumerating necklaces in maybe constant time per update. So I have start with this string, take the last thing, put it into the middle, and then yeah, so you do, so there's a sequence of simple local operations that will take you through all the necklaces, one element of each necklace, meaning one representative from each necklace. So there are some nice enumeration algorithms, there are some nice
But that doesn't give you.
yeah, that doesn't give what we need here. Here we need give me, yeah, you want to, yeah, right. So there, to find the middle necklace, you'd have to work your way all the way up, starting from the beginning. And it's not clear how to jump to that step immediately. And yeah, so somehow this is, yeah, so this is a bit of a messier algorithm. It takes n cube time. I think, yeah, most algorithms in this thing, they come up with really fast and clever algorithms for enumeration, etc. But yeah, yeah, for necklaces there are. Yeah, there are many different ways of enumerating in nice ways, and there are also enumeration algorithms for necklaces in of a fixed weight and unlabeled necklaces, and yeah, so there's a whole area where they study these heavily. So there's a book by Rusky on combinatorial enumeration, which has a bunch of nice examples where this problem apparently was mentioned as an open problem.
So you can also do fixed weight.
In this, you can also do fixed weight. Yeah, right, because the branching program can just recognize, yeah. But if you take this and try to make an enumeration algorithm out of it, which means list all of them, then this would be much slower than the ones that they get, yeah. Yeah, great, thanks. Okay, thanks.
Just press the button.
Ah, okay.
This is new.
Right, okay.